Hi everyone, my name is Mario, and today I'll be showing you a couple of really cool things that you could do with square numbers. The first thing I want to show you is what I like to call single-digit symmetry, where if you take all the square numbers from 0 squared all the way to 10 squared, the last digit of each of the squares will be symmetrical around a center point of 5 squared equals 25, where 4 squared equals 16, 6 squared equals 36, and the last digit of both those squares are the same, which is 6. And this will continue with 3 squared and 7 squared all the way down to 0 squared and 10 squared. But this does not just happen with 0 to 10, it happens with any grouping of 10. So if I were to take 14 squared and 16 squared instead of just 4 squared and 6 squared, I would get 196 and 256, where the last digit is also the same. This holds true even for groupings that are bigger than 10, like 50. So with 50, the center point is 25, and 25 squared is 625. But instead of single-digit symmetry, it's double-digit symmetry, where if two numbers are the same distance away from 25, then their squares will have the same last two digits. For example, 24 and 26 squared both end with 76. And we take 18 over here and 32 over here, and we square both of them. We get 324 and 1024, and they are both 7 away from 25. Another cool thing you could do with square numbers is just a faster method of multiplying two numbers. And you could do this by finding a difference in squares. So we have 8 squared, which is equal to 8 times 8, or 64. So what would happen if we subtract 1 from one of the 8s and add 1 to the other 8? So here we get 8 minus 1 times 8 plus 1, so 7 times 9, and we get 63. We do the same thing, except instead of minus 1, we would do minus 2. Instead of plus 1, we would do plus 2. And we get 6 times 10, which is 60. If we keep doing this, 5 times 11, 4 times 12, we get 55, 48, and it would go on for a little bit longer. Right, you notice that it keeps on going down, and it goes down in a quadratic pattern. Right, so what is the pattern? Well, it just so happens that it could be explained by a difference of squares. So we have 8 squared right here, which is 64. And if you notice, 63 is 1 away from 64. 64 minus 63 equals 1. All right? So 64 minus 60 would be 4, and 60 is the second number that we got. If we keep going down the list, we go 55 and then 48. 64 minus 55 equals 9. 64 minus 48 equals 16. Well, we can start to see a pattern here. These are all square numbers. So this is 8 squared. And we can rewrite all of these equations by subtracting this number instead of this number. So we can get 8 squared, or 64, minus 1, which is also 1 squared, so I'm going to write 1 squared, is equal to 63. And we could do the same thing. 8 squared minus 2 squared, or 4, is equal to 60. So now we can rewrite this to be equal to this. 8 minus 2 times 8 plus 2 is equal to 8 squared minus 2 squared, which is equal to 60. So you notice 2 is the number that we add or subtract to the 8. So we could think of 8 as our center point. So let's reverse engineer this. So we have 8 minus 2, which is 6, and an 8 plus 2, which is 10. So if we take these two numbers, what we would need to do is somehow find a way to get 8 from these two numbers, which is easy. We know we can find the average of these two numbers. 6 plus 10 over 2 is equal to 8. It just so happens to give us this. All right? And we know that the distance from 6 to 8, or the distance from 8 to 10, is also 2. Okay. So we can just do 10 minus 6 over 2. And this is its own little thing. I'm going to move this down a little bit. And this would be equal to 2, right? So we have 8 and we have 2. And we got that from two random numbers. And since we're squaring these, we're squaring both of these to get our product. It would actually just be 6 plus 10 over 2 squared minus 6 minus 10 over 2 squared. And notice it doesn't matter which order these two numbers go in, since we're squaring the product anyways. So 6 minus 10 would be -4. -4 over 2 would be -2. So we would either get 2 or -2, but since we're squaring it, we will get the same product regardless. And we would get 60. All right, which is the product of 6 and 10. This might not be very useful for things like 6 and 10, but it might be pretty useful for numbers like 17 and, 33, where you can't really come up with a product for those two numbers very quickly. But if you're able to find a difference of squares, you can find the product pretty quickly. So we can find the average of those two, 17 plus 33 over 2, and square it, minus 17 minus 33 over 2 squared equals some product, right? Which should equal 17 times 33. So let's simplify this. We have 50 over 2, so that's 25 squared, minus -8 or -16 over 2 squared, so that's 8 squared, so minus 8 squared is equal to their product. If we simplify this, 625 minus 64 is equal to 17 times 33. And then if we do some quick subtraction, we could find that the result is 561, I believe, which is equal to 17 times 33. So it's just a quicker way to find a product of two numbers that you might not know the product of immediately. And you could do this by finding a difference of squares, where any product between two numbers can be explained by one square number minus another square number. It is a little bit easier if both the numbers are odd, like here, or if both the numbers are even, like with 6 and 10, because then the average will be a whole number instead of, something 0.5. So if this was 6 and 11, then the average would be 8.5, and it would still work, but the numbers would be a little bit trickier, and it would require you to memorize square numbers that are kind of weird and kind of like unorthodox. Here I would memorize 25 squared and 8 squared, which are pretty easy to remember. But what happens if you have to memorize 11.5 squared? It's not as easy. But it is still a trick that you can use, and that's just something I found pretty interesting.